All right, today we're going to talk about something that sounds like it's straight out of science fiction, but is actually one of the most powerful ways we have to describe the real world. We're talking about complex numbers. So let's go ahead and dive into this hidden dimension of reality.
So to get started, I want to ask you a question that really bugged mathematicians for centuries. What happens when you come across an equation that, by all the rules you know, just can't be solved? Is that even possible?
Well, here it is. This is the equation. This is the locked door. In the world of numbers we use every day, the ones on a number line, positive and negative, this thing is impossible. And why? Well, think about it. When you multiply any of those numbers by itself, the answer is never, ever negative.
And that simple, unsolvable little equation, it actually points to a huge weakness in the numbers we're all comfortable with. It showed everyone that our so-called real numbers were, well, kind of incomplete.
I mean, really think about it. A positive number times a positive number is positive. A negative number times a negative number is also positive. There was just no number on that whole line that would give you -1 when you squared it. For a very, very long time, that was just the end of the story. Case closed.
But then, mathematicians had this completely radical idea. Instead of just seeing this as a dead end, they started asking, what if the number we need doesn't exist? What if we just invent it? And this wasn't about just solving one little problem. This was about blowing open a whole new dimension in math.
And just like that, the number I was born. We call it the imaginary unit, and it has exactly one job, to be the number that when you square it, you get -1. Now, the name imaginary, which we can thank Descartes for, was maybe a little unfortunate, because it makes it sound like it's not real. But it's a perfectly good mathematical tool, one that was built to solve a problem. So now that we have I in our back pocket, we can create a whole new kind of number, the complex number. And it's pretty simple, really. It has two parts. A real part, A, that's a number we already know and love, and an imaginary part, B, that's being multiplied by our new friend I.
And this is where it gets really cool, because these numbers now have a visual home, the complex plane. So instead of just a single number line going left and right, we now have two dimensions. The horizontal axis is for the real part, and the vertical axis is for the imaginary part. Every single complex number has its own unique spot on this plane.
And doing math with these numbers looks really beautiful. For example, adding two complex numbers works just like adding vectors in a physics class. You draw a line from the center to each number, make a parallelogram, and the diagonal of that box points you right to the answer. It's visual, it's intuitive, and it just works.
Okay, so we're in this new world of numbers. We're going to need a few tools to get around. And one of the most powerful is a really simple but brilliant idea that I like to call the mirror image trick.
It's officially called the complex conjugate. And here's all you have to do. For any complex number, you just flip the sign of the imaginary part. So the conjugate of a plus bi becomes a minus bi. It's as simple as that.
And if you look at it on the complex plane, it's just so elegant. The conjugate is the perfect mirror image of the original number, reflected right across that horizontal real axis. It's a perfect symmetry.
So, why do we care about this mirror image? Well, look what happens when you multiply a number by its conjugate. All that messy imaginary stuff, it completely cancels out, and you're left with a squared plus b squared. And that is always, always a plain old real number. It's like a secret escape hatch, back to the familiar number line.
And this little trick has some serious power. It's what makes dividing complex numbers possible. You see a scary-looking fraction with complex numbers? No problem. Just multiply the top and bottom by the conjugate of the denominator. The bottom magically becomes a real number, and the problem basically solves itself.
Now, inventing I did way more than just help us solve some tricky equations. It actually peeled back a layer on reality and showed us this hidden world of order and beauty that was sitting right there in mathematics the whole time.
Take something like de Moivre's formula. It builds this incredible bridge between complex numbers and trigonometry, two fields of math that you'd think had nothing to do with each other. The formula shows that raising a complex number to a power is actually the same thing as rotating it around the origin. It's this deep, totally unexpected connection. And that leads to this truly mind-blowing result. If you ask a question like, what are the 5/5 roots of a number? You don't just get 5 random answers back. You get the 5 points of a perfect pentagon. The answers to these equations have this gorgeous, built-in geometric symmetry that was totally invisible before complex numbers came along.
And this all builds to one of the most important ideas in all of mathematics, the fundamental theorem of algebra. It basically says that with complex numbers, there are no more impossible polynomial equations. Not a single one. It doesn't matter how complicated it is, it now has an answer. That one little key, I, unlocked all of the doors at once.
Okay, so this is all a really beautiful, elegant mathematical idea. But so what? Does any of this actually have anything to do with the real world? And the answer, amazingly, is yes. It's not just useful, it's absolutely essential.
It turns out this imaginary dimension is basically the secret language that the universe is written in. From the electrical engineering that powers our world and the signal analysis that runs our phones, to the absolute fundamental laws of quantum mechanics, complex numbers are everywhere.
Let's take electrical engineering. Complex numbers are used to describe how alternating current flows through a circuit. They let engineers wrap up resistance and reactance into one single value called impedance. And that makes the math for designing, well, everything from your phone charger to the entire power grid way, way simpler.
Your Wi-Fi signal, your GPS, the audio you're hearing right now, all of it is processed using complex numbers. They give us a really slick way to describe the two most important parts of a wave: its amplitude, that's its strength, and its phase, which is its timing.
And maybe the most profound example of all is in quantum mechanics. Complex numbers aren't just a handy tool here. They are literally baked into the fabric of reality at the smallest possible scales. The Schrödinger equation, the master equation that governs the quantum world, is fundamentally built on complex numbers. You cannot describe how an atom works without them.
Which really brings us full circle, doesn't it? We started this journey with a number that got the name imaginary, because it seemed like it only existed in our heads. But we've just seen that this number is indispensable for describing very real electricity, very real signals, and the very real quantum building blocks of our universe. So it kind of makes you wonder, if imaginary numbers are this essential for describing reality, how imaginary are they really?